I'd like to briefly bring up a couple of other classic probability examples in this video, the first one being the gambler's fallacy. Now, the gambler's fallacy speaks to the fact that a gambler's odds do not improve as they continue playing a game. And if you've ever been in a casino before, you've probably seen this in action. So suppose somebody's playing a slot machine in a casino and their odds of winning at the slot machine are 1 in 100. Well, that means the first time that they play the game, their chance of winning is 1 in 100. Now, regardless of what happens the first time, when they play it the second time, their odds of winning are 1 in 100. When they play it the 100th time, even if they've lost 99 times in a row, their odds of winning are still 1 in 100. Unfortunately, a lot of gamblers think that if they lose a lot in a row, that eventually the odds need to be turning in their favor, but the odds don't change. The odds of 1 in 100 suggest that in the long run, over years and decades and the history of people playing the game, yes, the game will pay out approximately 1 in 100 times. And sure, if gamblers sit at that slot machine long enough, eventually they're going to win sometimes. But they're also going to lose a lot of money in the process with that type of thinking. Now, the most famous example of the gambler's fallacy occurred in a game of roulette at the Monte Carlo Casino on August 18, 1913, when the ball fell in black 26 times in a row. And yes, that was an extremely uncommon occurrence, although it's no more or less common than any of the other 67 million plus sequences of red or black that you could get on a roulette wheel. But what happened that day was gamblers ended up losing tons of money because they started betting against black, reasoning incorrectly that the streak was causing an imbalance in the randomness of the wheel and that eventually you would need to be followed by a streak of red. But even after 26 times in a row of the ball falling on black, on the 27th spin of the roulette wheel, the chance that it was going to fall on black was going to be the exact same as falling on red. The odds were not going to increase for it falling on red, and unfortunately a lot of people lost a lot of money that day for that incorrect reasoning. Now, another classic probability example is known as the birthday problem. And what's cool about this example is it's not something that you would typically expect, but we can illustrate with some of the probability rules that you'll be learning in this module that this is in fact true. And it says that in a group of at least 23 people or more, there is more than a 50% chance that at least 2 people will share the same birthday. And again, I know when you hear that, you probably think there's no way, but I run this example in my class all the time where we typically have more than 23 people, and I would say more often than not, at least 2 people in my classes will end up sharing the same birthday. The interesting thing is, as that group starts to increase, as you move from 23 to say 30 people or 35 or 40 people or 50 people, the probability that at least 2 people will share the same birthday starts to go up quite a bit. And by the time you get to 50, 60 people, you're in the 90% range or so for the likelihood that at least 2 people will share the same birthday. So next time you're in a group of at least 23 people or more, you can think about this and even see if it actually works out. Okay, if you'd like a little bit more on the birthday problem, there is a link that I gave you in the notes. I would encourage you to check that out so that you can kind of see some of the math behind it. But a lot of that math is what you'll be seeing in this module. So hopefully after seeing some of these classic examples, it just gets you excited about some of the things that you'll be able to do once we're done learning this stuff here. Thanks for checking this out.